This video is on electron dot notation and Lewis structures. Electron dot notation is the precursor to a Lewis structure. This is a notation that shows only the valence electrons of an element by placing dots around the element symbol. We know that we can easily find the number of valence electrons of an element by looking at the group number on the periodic table. As you may remember, group 1A has one valence electron, 2A has two valence electrons, so on and so forth, all the way up to group 8A, which will have 8 valence electrons. In order to do this, there are 3 steps we must follow. The first step, you simply write the element symbol. The second step, by looking at the group number, you determine how many valence electrons the element has. And the third and last step is that you place dots around the symbol corresponding to the number of valence electrons. The first example here is boron. So you want to locate boron on the periodic table, and you will see that the symbol for boron is B. So I will just draw a capital B. Boron is in group 3A, which means it will have 3 valence electrons. I like to start at the top of the element, so I put 1 valence electron there, and then I like to go clockwise. So 1 would go here, and then 1 would go there. And those are your 3 valence electrons. For fluorine, fluorine is symbol F, and it is in group 7A, which means it has 7 valence electrons. Again, I'll start at the top, 1, 2, 3, 4. And now I can start pairing up because I ran out of room on all 4 sides. 5, 6, 7. And that is the electron dot structure for fluorine. So moving on from the dot structures, we get to Lewis structures. And these diagrams show the bonding between the atoms of a molecule. The electrons that are not involved in bonding will exist as what's called a lone pair. So down in this picture here, we have 2 fluorine atoms. The 2 electrons, the 2 dots between the 2 fluorine atoms, they are shared electrons. They are bonded electrons. The electrons that I am circling in blue, these are lone pairs. So you can see that each fluorine atom has 3 pairs of lone pairs. Or they each have 6 electrons that they're not sharing. Another way of writing, which you will see, this diagram right here, would be replacing the shared electrons with a dash. That dash represents a bond, and in this case, a single bond. And you will see that on the next slide. So a single bond is when there is 1 pair of shared electrons. Single bonds are the longest bond length. If you have a double bond, that is when you have 2 pairs of electrons shared. 2 pairs would equal 4 electrons. And the way to depict a double bond is to draw 2 hyphened lines. It almost looks like an equal sign. This is shorter than a single bond length-wise, but it is longer than a triple bond, so it's the in-between bond length. It takes more energy to break a double bond than it does a single bond. And then lastly, a triple bond, that is where 3 pairs are shared. That means there would be 6 total electrons shared there. And as you can imagine, this is the shortest bond length. A triple bond would look like that. Nitrogen is known to triple bond. Certain elements have more tendencies to bond singly, doubly, or triply. When we are drawing Lewis structures, there is a set of rules that we need to follow. And the rules will be posted for you to follow along with. But these are the rules for them. Something to really highlight is step number 5 here. These two spots here are exceptions, or these are added rules. So if steps 1 through 4 and then number 6 does not work, you need to refer to number 5. And I wrote these rules kind of to guide you through different scenarios. So we will refer to them as we do this. So draw the Lewis structure for CH3I. So the first step, you want to determine how many total valence electrons the compound has, or the molecule has. So C on the periodic table has 4. H has 1, but notice we have 3 H's. So we have to multiply that 1 by 3, and I has 7. Again, I'm getting those numbers just by the group number. So we have a total of 14 valence electrons that we need to use here. If you refer to your rules, it says that carbon is most likely going to be present in the center, if it is present. So we're going to put a C right there. And a lot of times it's nice, if you just read from left to right, it kind of tells you what is bonded to what. So attached to this C, there are going to be 3 H's. Now you want to be symmetrical when you can, meaning if I put an H up top, I want to put an H down low. Or if I put an H to the left, I want to put an H to the right. In this case, I have 3 of them, so I can't really be too symmetrical here on a 2D plane. So I'm just going to put 3 H's there. And then the I will go over here. And it says to connect all of those elements together with a bond. So I want to refer back to the rules so we can look at them. So step number 1 we did. Step number 2, notice we followed that. This is very important, that hydrogen will always have 1 bond from it. So notice here, why didn't I put this I onto one of the H's? Why didn't I put an I there? Well, because I knew that once hydrogen has one of those bonds, it is done. It cannot do anything else. And that is because it's in the 1s sublevel. And the highest electrons in the 1s sublevel is 2 electrons. And by hydrogen sharing 1 with carbon, notice it already has 2 there. So it cannot have any more. So you need to know the hydrogen can only have 1 bond coming from it. So I knew that I had to go there. I also know that most of the time, not all of the time, but most of the time, carbon will have 4 bonds from it. Again, it's not always, there are exceptions, but a lot of times that holds true. And then we connected all the elements together. So we did that. Step number 3 says to add unshared pairs of electrons to each nonmetal, except hydrogen and carbon, so that each is surrounded by 8 electrons. This is called the octet rule. So you want everything to have 8 electrons. Again, there are different exceptions to these rules. Some elements, sulfur and phosphorus are big ones, they can have expanded valence shells, so they can actually have more than 8. Or there are some smaller elements like beryllium that can have less than 8. Aluminum can have less than 8. But these are general rules. So I want to add dots to everything so they have 8 electrons except hydrogen and carbon, which leaves just iodine, right? So iodine right now, it just has this bond here, which we know counts for 2 electrons. That we could redraw this by doing this, and that means the same thing. So if I need iodine to have 8 and it already has 2, that means I need to add 6 more to iodine. That's what rule number 3 is telling me. Rule number 4 says count up the electrons and make sure that you used the number you started with. Make sure you used 14. So let's count these. Each bond counts as 2, remember. So this is 2, 4, 6, 8, 10, 12, 14. That matches. And again, 5 is our like exception rules, so we'll skip that for now. 6 says, be sure that all atoms except hydrogen have an octet, meaning 8 electrons. Notice carbon has 2, 4, 6, 8 electrons around it, and iodine also has 2, 4, 6, 8. This is the correct Lewis structure. Next one, draw the Lewis structure for NCl3. So again, we need to determine valence electrons first. Chlorine has 7, but we have 3 chlorines. So we have a total of 26 electrons we need to use here. So we have 1 N, we have 3 Cl's. Hopefully it's common sense that the N will be in the middle surrounded by the Cl's. I could have put this Cl up here, or I could have put the Cl's like this. It does not matter. If you can be symmetrical, you want to be. Rule number 3 says to add dots to everything so they have 8. So this chlorine would need 6. This chlorine would need 6. This chlorine would need 6. And that nitrogen would just need 2 because it already has 6 electrons. 3 bonds times 2. Now let's count them up. Let's see if we got our 26 here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We do. And last step, step number 6, make sure everything has an octet. They all do have 8 electrons surrounding them. So here we will run into one of our exceptions with rule number 5 here. So we have CH2O. So it looks like here we have 12 electrons we're going to use. If C is present, again, put that in the center and kind of read left to right here. Now, step number 2. Again, it's not an always thing like the rules say, but 99% of the time, carbon's going to have 4 bonds coming from it. So looking at this, carbon only has 3 bonds there. And there's no other elements to bond to it. Like, there's nothing else down here. So that looks strange to me. So a red flag's going off. But, however, let's just keep going here. It says to add dots to everything except carbon and hydrogen. So they have 8. So their oxygen now has 8. Let's count them up. Let's see if we have this 12, 2, 4, 6, 8, 10, 12. You may be thinking, okay, we're good here. Step number 6. Be sure all atoms except hydrogen have an octet. Our carbon does not have an octet. Our carbon only has 6 electrons around it, the 3 bonds. So that is an issue. It did not satisfy the octet rule. So look at step number 5 here. It's the second part. If an octet is not met, move 1 or more lone pairs to existing bonds between non-hydrogen atoms until the outer shells of all atoms are completely filled. Which means we know that the hydrogens are finished. Hydrogen can only have 1 bond, so it's not even worth looking at these guys. These guys are done. So what it's telling us to do is to take a lone pair from oxygen, any lone pair, doesn't matter which one, I just picked the top one, and move it to here. And what that does is that is just making oxygen share those 2 with carbon. So what's going to happen is those 2 that are coming down are going to form our double bond there. So notice we didn't use any more or less electrons. We still used 12 electrons. But now forming that double bond helped us satisfy the octet rule for carbon. And notice oxygen still has its octet. How about for C2H2? Looks like we have 10 electrons to use. We have more than one carbon, so they're both going to be central. And then we have two H's. Again, be symmetrical when you can be. So instead of giving one of the carbons two H's, give each of them one. Okay, right away, I'm looking at my carbon. We should have 4 bonds. So something is off here. We only use 6 electrons. So we don't want to put dots on C usually. You never put dots on H. So something weird is going to happen here. Maybe you see it. A double bond doesn't help us because carbon still doesn't have 4 bonds, but a triple bond will help us. So what does that do? Did we use all 10? 2, 4, 6, 8, 10. We did. Does everything have an octet? This carbon has an octet because there's 4 bonds, and 4 times 2 is 8. This carbon has 4 bonds. 4 times 2 is 8. We did satisfy the octet. In real life, Lewis structures of very many compounds and molecules are very long. So here's one, just a bigger, more intense Lewis structure, which we'll get to later in the course. But you can see, double bonds here. You can actually see this is an ion separated. That's a little bit different. But I just wanted to give you exposure to bigger Lewis structures out there in the world. This Lewis structure, you can see this is kind of in a ring, or it is in a ring formation here. So that's something special as well. I encourage you to think of something you use in your everyday life or something you eat. Like look up vanilla, for example, and just look up the Lewis structure of different things you come across in your everyday lives. Look up the Lewis structure on Google. I think you'll be pretty surprised with what you find.